Okay, so now we are ready to prove the complete theorem. Suppose T from H to H is a compact self-adjoint operator on a Hilbert space. Then there is an orthonormal basis of eigenvectors of T. Each non-zero eigenvalue of T has finite multiplicity. The idea is very simple. We have already established the existence of an eigenvector. That, as I said, is the most difficult part of the argument. That is where the weak compactness, namely every norm-bounded sequence has a weakly convergent subsequence. That property was crucial. We used that property and we proved the existence of the eigenvector. So now we must apply the zones lemma and we must take a maximal orthonormal set of eigenvectors. How does one do this? You have to use either the zones lemma or the Hausdorff's maximality theorem. What is the Hausdorff's maximality theorem or what is the zones lemma? Suppose I got a partially ordered set. So what is my set? My set is the collection of all orthonormal subsets of eigenvectors of H. So my family of sets, pay attention, my family of sets consists of orthonormal sets of eigenvectors. And this collection is non-empty because we have proved the existence of an eigenvector, and so we have a eigenvector V naught of unit length. So the singleton set V naught is automatically an orthonormal set of eigenvectors. Now this set is partially ordered by inclusion. Now that it is partially ordered by inclusion, set theoretic inclusion, Hausdorff's maximality theorem says that maximal chains exist in any partially ordered set. So take a maximal chain containing this singleton V naught. We will now show that this maximal chain must give you a orthonormal basis. So now you have got a maximal chain. What is the maximal chain? Any two sets in this chain are contained in one or the other. Suppose I take C1 and C2 in this maximal chain. Either C1 is contained in C2 or C2 is contained in C1. That is the meaning of chain. And it is a maximal chain, that it can't be enlarged any further. Take the union of all the sets in this chain. Every subset is a orthonormal set. And so this union will also be a orthonormal set. And all the vectors are eigenvectors. So this union will be an orthonormal set of eigenvectors of T. And it's maximal. This chain is maximal. I can't enlarge it any further. So now we shall show that this union of all the sets in this maximal chain is a basis for H. What is the meaning of saying that B is a basis of H? It means you take the linear span of B and take its closure. I am supposed to get the whole of H. Suppose B is not a basis, that means that the closure of the linear span of B, call it Y, Y is not the whole of H. So Y perp is non-zero space. There are non-zero vectors in Y perp. So now I got this nice non-trivial Hilbert space Y perp, and I restrict my operator T to Y perp to get an operator from Y perp to Y perp. But this operator Y T restricted to Y perp, it has an eigenvector V naught of unit length, which will also be an eigenvector of T, because this new operator T from Y perp to Y perp is a restriction of T from H to H. So any eigenvector of the restriction will be an eigenvector of the original operator. So V naught is now an eigenvector in which space? In Y perp. Where is B contained? B contained in Y. So, V naught is orthogonal to B. So, B union V naught is strictly larger than B, and I can adjoin this B union V naught to my maximal chain, and I can get a strictly larger chain contradicting the maximality of the chain. And this contradiction proves that B is a basis. So, we have a orthonormal basis of eigenvectors of T, where T from H to H is a compact self-adjoint operator. The spectral theorem is completely proved. As we see, the last part was purely algebraic. There is no analysis involved here. The difficult part was to produce an eigenvector and to identify the supremum or the Rayleigh quotient as an eigenvalue. For that, the compactness of the unit ball in the weak sense is needed. So, now let us show that every non-zero eigenvalue has finite multiplicity. Let lambda be a non-zero eigenvalue and let V lambda be the eigenspace. We have to show that V lambda has finite dimension. Let U naught be the closed unit ball in V lambda. We have to show that U naught is compact, because if you take a normed linear space, the unit ball will be compact if and only if the space is finite dimensional. So, if we show that the U naught is compact, we are done. So, how do you show that U naught is compact? We show it sequentially compact. Take a sequence of vectors in U naught, then T V n will be equal to lambda V n, but lambda is non-zero, and so I can say V n equal to 1 upon lambda T V n. But T V n has a convergent subsequence because T is compact. So, let us call this convergent subsequence T V n k. So, V n k will be 1 upon lambda T V n k. 1 upon lambda T V n k converges. So, V n k converges. So, we have proved that every sequence has a convergent subsequence. So, the unit ball U naught is compact. Now, the same argument can also be used to show that given any positive real number C, there are only finitely many eigenvalues lambda whose modulus exceeds C. Suppose not. Suppose you have infinitely many eigenvalues whose modulus exceeds C, and for each of these eigenvalues pick a corresponding eigenvector of unit length. So, we will have what? We will have a infinite sequence of unit eigenvectors corresponding to distinct eigenvalues, and we know that eigenvectors corresponding to distinct eigenvalues are mutually perpendicular. So, the distance between any two of them is going to be root 2. So, they cannot have any convergent subsequence on the one hand. But let us look at the image vectors T V n. What are the image vectors T V n? T V n equal to lambda n V n, or V n equal to 1 upon lambda n T V n. But T V n has a convergent subsequence T V n k, and lambdas all exceed C in absolute value. So, 1 upon lambda n k will be less than C in absolute value. So, 1 upon lambda n k into T V n will also converge, perhaps after passing to a subsequence. So, this sequence of unit eigenvectors which are mutually perpendicular has a convergent subsequence, which is false because distance between any two of them is root 2. So, we have established that for a compact self-adjoint operator on a Hilbert space, there is an orthonormal basis of eigenvectors. Each non-zero eigenvalue has finite multiplicity. The eigenvalues form a countable set, and they can only accumulate at 0. They cannot have any other limit points except 0, because outside, for every C positive, there are only finitely many eigenvalues whose absolute values exceed C. We also seen that the eigenvalues can be generated by successively maximizing the Rayleigh quotients analogous to the case of a real symmetric matrix. So, the complete analysis is done for a compact self-adjoint operator on a Hilbert space. So, now let us look at how to apply this general theorem to Sturm-Liouville problems. Our main concern is y double prime plus lambda rho x y equal to 0 with Dirichlet boundary conditions or with Neumann boundary conditions. That is our main concern, and that is all that we are looking at. For that, let us select an appropriate Hilbert space. I am going to call it the weighted L2 space. So, what is a weighted L2 space? Let us take a rho from 0 1 to r, a continuous function, a density function for a vibrating string, for example, and we will assume that the rho vanishes on a set of measure 0, that the zeros of rho form a set of measure 0. We are going to assume that rho is also positive. Okay. Then L2 rho of 0 1 is a set of all functions f from 0 1 to r such that integral 0 to 1 mod ft squared rho t dt is finite. So, essentially instead of working with Lebesgue measure, and I am looking at the square integrable functions with respect to this new measure rho t dt. That is a vector space over the reals, and I can define an inner product. Take f and g to be two functions which are in L2 sub rho. What is the inner product? Integral 0 to 1 ft gt rho t dt. With this, L2 rho of 0 1 is a Hilbert space. The proof is analogous to the classical case with cosmetic changes. This is the correct space to look at when you want to study the Sturm-Liouville problem with Dirichlet boundary conditions. So, now let us make an observation that the operator t from L2 rho 0 1 to L2 rho 0 1 given by Tf of x equal to integral 0 to 1 kxt ft rho t dt, display 7.26 in the slide. I am going to assume that the kernel k is continuous on the square 0 1 cross 0 1. Then this operator t is going to be a compact operator on L2 rho of 0 1. Now, when will this compact operator be self-adjoint? It will be self-adjoint precisely when the kernel is symmetric. Kxt is the same as ktx. Proof is exactly the same as in the case of the L2 of 0 1, and so I shall leave it to you. We now transform the Sturm-Liouville problem into an eigenvalue problem for a compact self-adjoint operator of the form 7.26. So, let us take 7.27 y double prime plus lambda rho y equal to 0, y of 0 is 0, y of 1 is also 0, and let us assume that lambda is an eigenvalue. We know that 0 is not an eigenvalue, that we know for sure. So, compulsorily lambda is not 0. Integrate 7.27 twice. First time you are going to get y prime of x equal to y prime 0 minus lambda integral 0 to x y of t rho of t dt. Integrate again, y of 0 is 0, y of x equal to x y prime 0 minus lambda integral 0 to x ds integral 0 to s y of t rho of t dt. Now, we must switch the order of integration, and we get what? Y of x equal to x y prime rho minus lambda times integral 0 to x y of t rho of t dt integral t to x ds. The inner integral of course can be integrated, and so finally we get the explicit formula y of x equal to x y prime 0 minus lambda integral 0 to x x minus t y of t rho of t dt. Now, we have to incorporate the boundary condition. What is the boundary condition? Y of 1 equal to 0. So, when you put y of 1 equal to 0, we immediately get y prime of 0 equal to lambda times integral 0 to 1 minus t y of t rho of t dt. So, now substitute this back into the previous formula. What do we get? Y of x equal to lambda integral 0 to 1 x into 1 minus t into y of t rho of t dt minus lambda times integral 0 to x x minus t y of t rho of t dt. Combine the two and write it as lambda times integral 0 to 1 g x t y t rho t dt 7.28 in the displayed slide, and g of x t is the Green's function for the boundary value problem. And so, now the solution operator y has been expressed as an integral equation, and let us look at the Green's function a little carefully. If you write out the expression for the Green's function, we have already done it in the past and I will not repeat the details, you can write it yourself. G of x t equal to t times 1 minus x if t is less than or equal to x, g of x t equal to x into 1 minus t if x is less than or equal to t. So, we see that the Green's function is symmetric, and 1 upon lambda is an eigenvalue for the compact self-adjoint operator t from L2 rho to L2 rho given by Tf equal to integral 0 to 1 g of x t f of t dt. Look at this equation, look at the last equation 7.28. It says that y of x equal to lambda times ty or divided by lambda, and we say that ty equal to 1 upon lambda y, that is 1 upon lambda is a eigenvalue for this operator 7.29. So, what have we proved? We have proved that if y is an eigenfunction for the Sturm Liouville problem with eigenvalue lambda, then 1 upon lambda is an eigenvalue for the operator t given by 7.29. Conversely, we want to show that if y of x is an eigenfunction for the operator 7.29 with eigenvalue lambda inverse, then y is a eigenfunction for the boundary value problem with eigenvalue lambda. Okay. So, let us do the following. Let us take 7.29. 7.29 will read ty equal to lambda times 0 to 1 g of x t y of t dt. Ty equal to integral 0 to 1 g of x t y of t rho t dt. So, differentiated once, what are you going to get? Y prime of x equal to lambda times integral 0 to 1 g prime x t y t rho t dt. But the Green's function can be differentiated. We have the expression for the Green's function over here in this slide. So, differentiate with respect to x, and we put that over here, and we get y prime of x equal to lambda times minus integral 0 to x t y t rho t dt plus integral x to 1 minus t y t rho t dt. Differentiate again, you get again two terms, and it simplifies to y double prime equal to lambda rho x y x with a minus sign. So, we see that y satisfies the differential equation with the Dirichlet boundary conditions. How do we know it satisfies the Dirichlet boundary conditions? Remember, what is the equation? Y of x equal to lambda integral 0 to 1 g of x t y of t rho of t dt. Put x equal to 1 and put x equal to 0. When you put x equal to 0, g of 0 t. What is g of 0 t? Look at the second expression for the Green's function. It disappears. What is g of 1 t? Use the first expression in the Green's function. Again it disappears. So, y satisfies the boundary conditions. So, we have proved that there is a bijective correspondence. Every eigenfunction for the operator t is an eigenfunction for the boundary value problem, and every eigenfunction for the boundary value problem is an eigenfunction for the operator t. Only thing is that the eigenvalue for the boundary value problem will be lambda, and then the 1 upon lambda will be the eigenvalue for the operator t. So, the eigenvalues become reciprocals, eigenfunctions are the same. So, what have we proved now? We have proved theorem 77. The Sturm Liouville problem y double prime plus lambda rho y equal to 0 with y of 0 equal to 0 and y of 1 equal to 0 has a countable set of eigenvalues tending to infinity. Each eigenvalue is simple, and the eigenfunctions form a complete orthonormal basis for L2 rho of 0 1. In other words, every function f in L2 rho of 0 1 can be expressed as a Fourier series f equal to summation n from 0 to infinity Cn yn, where yns are the eigenfunctions for the Sturm Liouville problem. So, we have completely clarified the meaning of eigenfunction expansion for a Sturm Liouville problem with Dirichlet boundary conditions. Same analysis can be carried over for the Neumann boundary conditions also, and this completes this module on abstract Fourier analysis. We have looked at the classical material of module 5 and we have looked at it in the light of functional analysis. So, we looked at certain aspects of Fourier analysis in the light of functional analysis.